Hey folks, welcome back to part two. Sorry for that very brief ending on part one. As I told you folks before, I only get 15 minutes for these. For some reason, my timer was invisible. So I was blabbling on about, I think, some of my previous research looking at pet products. Okay, so we'll kind of overlap. So let's suppose, once again, that we are interested in comparing the mean of ounces of food for various breeds of cat. So when you do an ANOVA, you will get something that looks like this. You'll get a chart of means for each of whatever it is you're trying to compare. In this case, we're looking at breeds of cats. N represents, once again, the sample size. So this would be the number of pieces of data that you have. Generally, you're given the mean and then the standard error for each particular category. Okay. But probably just as important, you are given the ANOVA table. Okay, you might remember in part one, I was suggesting that it's unique in the sense that even though ultimately what we're interested in is FSTAT, you are given some information in this ANOVA table. Okay, once again, it's not extremely important that you understand what all this means, even though I'm going to spend a little time kind of explaining it to you. But at the end, it's going to basically be as it was with the T test, and that is that it's going to be the FSTAT and then the p-value. Okay, but let's not get ahead of ourselves. So let's see if we can't make sense of some of this other stuff. What you see in this first, well, it's not the first column, it's going to be the third column, SS. It's not some Nazi thing. It is the sum of squares, okay? In this first area, right, treatments, this would be the amount of variance that would be explained by the differences, right? So, one of the things that's unfortunate about this ANOVA table is that it's not consistent with what we just talked about. So sometimes this is going to be called the between, right? And this is going to be called the within. Okay, so hopefully you make that connection, because this really is a telling us of the amount of variance that is between groups. Okay, and this would be the amount of variance that is within groups. Statisticians are notorious for using synonyms, so here it's called treatments and error. But once again, the top is almost always between, and what comes on it is always within, and then there's normally a total. Okay, so this would be that. So this would be just an estimate of that variance. I'm sorry, estimate of the variation. The actual variance would be what happens when you divide the sum of squares by something called the degrees of freedom. You can think of this as kind of a way of adjusting the n. Right? So remember, as with a mean, right, you normally divide the sum of something, right, by n, right? And that's what you do to get a mean. In this case, it's the sum of squares being divided by the degrees of freedom, which is an adjusted n, and that gives you something called a mean square. This would literally be what the variance is, okay? So this would be the variance between groups, and likewise, the bottom, we take the sum of squares there, that's divided by the degrees of freedom, okay, and that produces a mean square for error, or once again within, which once again is sort of the variance. So we really have two variances here. We have the variance between, and then we have the variance within, okay? And so the F ratio or FSTAT, okay, I guess I got ahead of myself. Sorry about that. But this basically explains the mean square for error. Okay. And then once again, if you ever had to do this stuff by hand, and you do not in this class, so don't ever worry about it. One way to check your work, right, make sure that you haven't messed up on calculating either the sum of squares or the mean squares, which can be calculated by hand, is that these things ultimately should add up to what the total is, okay, which has a separate variable. So it allows for cross-checking for people who have to do it by hand. That's a moot point here for you folks, because the computer's going to do it, and it's going to do it right every single time. Okay, but if you suspect that the computer is wrong, just look at this table. Okay, the between and the error should add up. 3 plus 100 is 103. That adds up. I'm sure if we added all that stuff together, we would get 260, 6150. At this point, there's no need to carry this out because you've gotten 2 points, which are the main things that then produce the variance. So that's really how this table is structured. Okay? All right. So let's talk about the F, which is what we're trying to get to here. This is what I'm trying to get to. If you remember, it's the variation between groups divided by the variation within groups. Okay, which is, once again, that variation is the mean square. Here the variance is called mean square. The treatment's divided by the mean square error, which gives us this 267. We're rounding to 2.53, even though I've rounded to 2 places here. When you're doing this work, if you ever do this by hand, once again, you shouldn't be doing it by hand. If you ever do it, then you should probably leave out 3 or 4 decimal places. Okay, and it gives us an F ratio of 1.06. Okay, if we were to round. Okay, cool thing is that the computer will generate that p-value here. Okay, and remember the rules about p-values. If a p-value is less than or equal to 0.05, it would be significant. Remember, 0.05 is our alpha level. Okay, and what we're saying is that the probability of obtaining that F ratio by chance is less than 5 times out of 100. Okay, so therefore we're going to take that type 1 risk and error and say, hey, that's real. Okay, we're willing to risk it for 5%, but we're not willing to risk it for anything above 5%. We're not going to be that risky. In this case, the p-value is 0.37. That's way over our 0.05 level, right? So we're not going to take that risk, and therefore we're going to reject the idea, right, that there is a significant difference between these brands of pet food. Okay, if you look at those means, right, the story kind of tells it, right? They're all within the range of 5. Okay, so you can pretty much eyeball that and test and see for yourself that there really isn't much variation. But we need to test that, right? We need to know sometimes things that look like they're very similar can in fact end up being statistically significant, which is why you can't just eyeball the means every time one way or the other. Okay, so I was saying earlier that there's lots of ways in which people talk about variation. So this idea of variance between groups, sometimes it's called variation due to treatment, as you saw in that ANOVA table. Sometimes it's called explained variation. Sometimes it's called factors. Depending upon which statistical software you use out there, you might find any of these synonyms, okay? With regard to the variance within groups, sometimes it's called error, as you saw in the with StatCrunch. Sometimes it's called the unexplained variation, and in some statistical software packages it's called residual, right? Unfortunately, we couldn't get all these people in a room together and agree on what the heck to call these things, so they're called different things depending upon the software package that you use. Okay? So analysis of variance. It's called that. Hopefully now you have a sense of that because we're looking at the ratio of variation between and within groups, right? So this is what's happening underneath the engine, so to speak. Now remember what I told you, if you didn't understand anything I've said, right, for the last, what would it be, 10 minutes, okay, you can still work this out because really all you have to do is follow the steps, which I'll talk about here in a little bit. But once again, one more point about what's happening underneath the hood. If you recall, variance was one of those things that you learned as sort of a step to getting the standard deviation. Okay, and you see how now this sort of fits in. Variance is equal to the sum of squares, which is what we had in the table, divided by n minus 1. Okay, that n minus 1 is actually something called the degrees of freedom, which is also a part of that table. Okay, all right. And more information that you probably don't need, but both the variance and the sum of squares measure how much the data varies from the mean. Okay, so let's get down to the nitty-gritty part, right? How do you do this, right? Even if you don't understand what's underneath the hood, you can do it. Okay, so let's do it. So conducting an ANOVA is matter, and let's give you an example, right? Researchers randomly assigned 36 bags of popcorn, each to be popped with no oil, medium oil, and maximum oil. right? So for you popcorn lovers out there, right, this would be a practical usage of the ANOVA, okay? So once again, what would be our null hypothesis? It'd be that there's no difference, right? There's not, the null is going to say, hey, it's not going to be any difference with respect to how many kernels gets popped, okay? The alternative is that, hey, there's going to be a difference somewhere, right? That there's going to be at least two of these means are going to be different from each other. And so, there is some assumptions that are talked about in your book. I'm not going to go over them that deeply because I'm running out of time here. But there's assumptions about randomness and independence of observations. There's assumption about normality. If you don't understand that, contact me. Most of the time, this test is robust. Okay, so you run it, and lo and behold, this is what you get. Okay, look at our F value, which is 3.89, and look at the P value. And remember the rule. Okay, if the P that we get is less than or equal to 0.05, which it is, right, we're going to reject the null hypothesis and we're going to accept the alternative hypothesis. So once again, the way we're interpreting the F ratio is no different than how you interpret the T or any other thing, right? If that p-value is less than 0.05, it's significant. So what would that say? Hey, there really is a difference between the amount of oil that you use in terms of kernels popped. I guess that's what that data reflects. Or maybe it reflects actually the amount of bad kernels that are popped. I don't know. So one of the big things about this is interpreting it, right? Running it is easy. It'll take you all about 2 seconds once you figure out where it's found in StatCrunch. So you'll spend most of your time looking at that output and trying to interpret it. So what we say, we can conclude that the amount of oil used is a factor for the mean number of kernels that are popped. Okay, since it was a controlled study, in other words, we randomly assigned people, we can actually say something about causation, right? Because of an experiment. Changing the oil amounts affects the number of kernels that are popped. I said that kind of cryptic, so I'll say it better. Changing the oil amounts affects the amount of kernels that get popped. Okay. And once again, ANOVA is based upon some of those assumptions that I briefly mentioned there. So if those assumptions aren't correct, then you can't really put much stock in the outcome of this. One of the good things about most statistical packages is they actually now check for those assumptions. So it really isn't up in the air. You'll know if you violated normality or equal variance or any of those things that your chapter talks about. Okay, so, all right. Let's talk about post hoc tests. Okay? So the problem is that once you have a significant F, you're only halfway to the goal. And it goes back to that point that I mentioned way earlier, right? When we talked about the fact that we're kind of testing all these hypotheses all together. And so the problem is that if I get a significant F, I still don't know where the differences are. Right? So for example, it's not clear to me if the differences that we just looked at, right, are between the moderate amount and the maximum amount, or between the no amount and the moderate amount, or between the maximum and the moderate. Right? It's not clear where those differences are, which is why when you run an ANOVA, it just tells us that there's a difference between the means, but it doesn't tell us which means are different from each other. Now, this whole thing about Bonferroni, you could do that if you wanted to do that, but nobody does that. Okay, and so the solution that's introduced in your chapter is something called Tukey's honestly significant difference. Sometimes we just call it Tukey's HSD. Now, I will tell you that there's like 26 of these different post hoc analyses, so thank be to God they just gave you one. Okay, I would tell you one of those My Day stories, but I've only got so many minutes left to finish this, and I'm going to run out of time. Oh no, gotta help. So step by step, check conditions around ANOVA. Run the ANOVA using the computer to find the p-value. If the p-value is greater than alpha, there's no evidence, right? So you stop there. If the p-value is greater, right, then you would use this Tukey HSD. It's going to help you to find where the differences are. And you can do it looking at either significance levels or confidence intervals. I'm going to do one just looking at confidence intervals. Hope I can get this in, right? So carnival operator is interested in whether the season is a factor, meaning amount of money. I'm not going to get enough time. So we'll continue this.